Hello, I'm Katie Steckles.
And I'm Peter Rowlett. Katie, what's our mathematical object today?
Today, our object is a pair of skipping ropes.
Okay.
This is not normally...
It is mathematical?
It is. It's not a creature normally seen in pairs. They usually occur singly, but in this case, having two skipping ropes allows you to do a really nice maths demo.
Okay.
So this is a thing that was done in a maths lecture by John Conway, and it relates to the theory of tangles. So if you have ropes, you can obviously get them tangled in various different ways, and there's a particular, I guess, set of moves that you can do with a pair of ropes, which gives a really, really nice underlying mathematical structure. And I sort of originally saw this when I was knocking around with maths busking people doing tricks, and we were discussing whether we could do this as a busking trick in the street, because it's genuinely a really entertaining thing to watch. So the idea is that you have four people standing in a square, and the two skipping ropes, the ends of the ropes are being held by the four people. So the initial state is that the two ropes run, I guess if you're looking at the four people from above and it's like a square, they're running horizontally across the top and bottom of the square.
Okay.
And then there are two moves that you're allowed to do. So one of them is a twist, where, I guess again looking at the square from above, the person in the top right swaps ropes, or swaps places, I guess, with the person in the bottom right. So you twist the two ropes around each other. Yep. And I guess it's important that every time you do that, you do it in the same direction. So whoever goes underneath every single time. And there is also a move called a turn, where all four people walk round one move round the square. So you're kind of rotating the square through 90 degrees. And again, that will always happen in the same direction whenever it happens. So they keep hold of the ropes, but they just walk around in a square.
And does that tangle the rope?
That doesn't tangle the ropes, but it changes
the
way that they're connected. Yes, so it's a different two pairs of people.
Mm-hmm.
So these are the two possible moves. So the only way to tangle or untangle is to twist, and then you can also turn, which will then affect what the next twist does.
Right.
And they're sometimes called rational tangles because you can associate with each tangle a rational number. So the untangle, I guess, the original state with the two horizontal ropes is represented by 0.
Right.
A twist will add 1 to the tangle number, and a turn will change a tangle number x to -1 over x.
Okay.
So these are the two operations you can do. So you can get to all the rational numbers this way, and I guess you can prove that those two operations get you from 0 to any rational number.
Right.
And you can also tangle up the ropes and keep tangling, and you can continue doing a turn and a twist in the same direction. And as long as the number gets back to 0, the ropes will be untangled. Right. Because it represents the same state.
Yep.
And it's sort of weird, because you can imagine that if you're only twisting in the same direction, you're never going to be able to untwist those twists. But I guess you could notionally think, okay, if I twist it once and then do 2 turns, I'd be facing the other way, and then I could twist and that would untwist it, or something along those lines. So you end up with the ability to do quite a nice performative trick, which I think is what Conway did in the lecture, which is to say, okay, I'm going to cover up the middle section of this. So there's like a plastic bag or something that goes over the ropes in the middle. And someone is going to give directions to these people in the form of saying the word twist or saying the word turn, so that we get a nice tangled knot in the middle. And it could be any combination of things, but somehow Conway is keeping track of what the rational number is associated with this thing. Yep. And once you get to that point, all you need to do is work out what sequence you then need to do to get that back to 0.
Right.
And once you've done that, you can take the bag off and the ropes will just fall apart because they're untangled. So that's quite a nice, collection of things in terms of a reveal and what have you. You could even leave the bag off until you're happy that it's sufficiently tangled and you can see it getting tangled up, and then you cover it up, and then the moves are all done to reveal the final thing. But it's just this really nice interplay of a physical object that people will enjoy watching and playing with, and you're physically holding onto the ropes, so it's kind of tangible, but also this beautiful structure which underlies the whole thing, and it's just really nice. So the first place I came across this was one of the University of Manchester summer schools had various little projects that sixth formers came in, and they had like an afternoon where they worked on a particular project that one of the lecturers had proposed, and this was one of them. And they just brought some sets of ropes and bits of things that people could play with, and the question was, can you sort of deduce this, given these two rules, can you deduce some things about this system and solve various little questions and problems that they'd kind of built a little story around it to take them through some nice thoughts. But it was just, That was the first thing I saw, but you can also, I think, watch the video of the whole lecture with Conway online, and there's transcripts of it in various places. Okay. And it's just, I think it's a really nice thing.
So can you convince me? So you can turn a number, you can add 1 to it, and you can make it -1 over itself?
Yes. And
can you sort of convince me that gets you to all the rationals?
Not quickly. I guess, yeah, it's sort of, it feels right because you've got the ability to, you can take the numerator as high as you want and then turn it into the denominator.
Yeah.
And as long as you do that an even number of times, you can get any positive number, and, an odd number of times will get you any negative number. And, something along those lines, maybe.
Yeah, that makes sense. And then if you have a tangle that is number X, what is the strategy for getting that back to 0?
Yeah, I think because I've had a go at trying to do this as a busk, and sort of said, challenge me, find a thing and see what I can do. And I've had to sit and try and work out a pattern to do to fix it. And there's a little bit of sort of trial and error and messing around with it. But you get to sort of see things that you know how to get home from, and that kind of thing. But I think in general, I'd end up with some kind of negative number, and I would keep adding 1 until I was above 0, and then make it negative again. And that kind of got me closer and closer to 0 somehow. So I guess what you really want is to be near a negative integer, and then you can just add your way up to 0.
Because I'm trying to think, like if you're at 2 and you do a twist, you're now at -1/2.
Yeah. And then you add 1, so you're at +1/2.
Yeah. And
then you do -2. Because you do -1 over 1/2, which would be 2, and then you can just add 1 twice.
Oh yeah, okay, yeah.
As soon as you get to a negative integer, you're fine.
Yes.
And you get kind of near to 0, and then you do something that puts you just above 0, and that gives you the ability to, I don't know.
Yeah.
It might be worth a play with if anyone's sat at home thinking, I wonder.
Yeah.
Yeah.
That's interesting.
Yeah, I guess it sort of links into the whole area of knot theory and talking about the way that things connect together. And obviously this is a very constrained set of things, because obviously given 2 ropes and 4 corners, there are any number of things that you can do. And the rational ones are precisely the ones that can be reached from twists and turns. So, I guess in the same way that you there's an analogy with the fact that you can get from rational numbers to other rational numbers, but the irrational numbers are somehow not gettable from there. And it's sort of a particular subset of the possible tangles that work for this problem.
Yeah. And that makes sense, because no amount of dividing will get you to an irrational. So
yes, well, exactly,
definition. Yeah. Oh, well, that's nice.
Yeah, so we've because with the busking thing, people tying each other up with stuff is a classic sort of way to get people engaged. Not just physically, also they can't leave for that reason.
Tell me about busking then.
It was there was a project several years ago to do more mathematical busking, so sort of to take maths ideas and get people talking about maths and do things in the street and at events, and sort of kind of engage people with the kinds of things that mathematicians enjoy showing each other and going, oh, this is interesting, I'm going to tell someone else. In the same way that I guess a normal person would share like a joke or a story they've heard, you could share a piece of maths. And we wanted to sort of empower people to do that. So But
this isn't a sort of in the corner of a railway station, somebody's doing some maths for money.
Well, I don't think we ever really made any money with it. I think someone put £1 in a hat once out of pity. But we were kind of at science festivals or at events and things like that where people wanted some entertainment. So it was more cabaret than pure busking, I guess. But it was using a lot of the ideas of kind of engaging an unengaged audience and that kind of thing that buskers have to deal with. But yeah, there were quite a few busks that were sort of topological or otherwise rope related, because there's the classic so Christopher Zeman was the first person to do one of the RI Christmas lectures about maths. I think he was the first, and in that he did a thing with 2 ropes, which was a slightly different trick where you attach a rope between someone's hands, so you kind of put a rope round their wrist with a loop, and then you have the same thing on another person, but the two ropes are actually twisted around each other, and the challenge is to try and get the 2 people separated without taking the ropes off their hands. And it's a really nice little bit of topology, because the the first conclusion you come to is that obviously if you've just got 2 linked circles, which is what it appears you have, there is no way to untangle that.
Yeah.
But then there's also this little gap. There's a kind of a gap between the rope and your wrist. And even if you're not allowed to take it off your wrist, you can maybe push a bit of rope through there or do something clever. Yeah. And I will leave it as an exercise to the reader to work out how you would actually untangle that, if you can imagine it.
Yes.
But it's, again...
It's a topological trick, because there's something of the... you think this bit is the inside, but actually it could also be the outside.
Topology. And the sort of... The initial conclusion that I won't be able to do this by stepping through the someone else's arms or whatever.
Yes.
You do end up, if you give people this as a challenge, you end up with lots of hilarious kind of people trying to climb over and crawl underneath each other's legs and that kind of thing, and none of it is going to work. And I've seen this where you put it on 2 mathematicians and they just stand there thinking like, oh, you're no fun.
Yes.
Do it properly. But there's that, and then there's other ideas that we did around, if you're holding 2 ends of a scarf, can you tie a knot in it?
Right.
Again, the answer to a topologist is obviously no. But if I give you the scarf and then cross my arms in a particular way and then ask you to pass me the scarf back, I can take the ends such that the knot in my hands can then be transferred to the knot in the rope. So that was a nice one. We also played around with a thing around, I don't know if you know the picture hanging puzzle, where you have to wrap a piece of string around 2 nails and then hang a picture on the ends of the strings, such that if you remove either of the nails, the picture falls down. And we did a couple of things with that. We had a big long sort of silk ribbon that was quite gentle and not going to hurt anyone. We'd say, like, put your arms out and we'll try and do a rope through around all your arms, such that if one of them pulls out, we can take the ends of the ribbon and pull them, and everyone will be untangled. That was quite fun. And I think we did legs across 2 tables once. At the Mass Jam gathering, we had enough enthusiastic people who were prepared to sit there and be laced together using a big long ribbon. And we did 5, and it worked, because the one person who had one leg in the game could remove their leg, and then the rest of it all just unravelled.
Yeah.
So,
that's cool. Good, right. So we should say we are... I'm Peter Rowlett on Twitter.
I'm at Steckles on Twitter.
And we both blog at aperiodical.com, which is also where you can find more episodes of this podcast.
And if you'd like to get in touch with us, if you have any questions or comments or any suggestions for topics or objects that we could talk about in future, you can get in touch by emailing objects@aperiodical.com.
The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons.